human skin 0.95. What else? Our soil is 0.96. Our soil also is good in emit the heat by radiation. Okay, so so this emissivity is properties. Okay, I can say it's a properties that can decide how much the radiation produced by surface. Okay, by a surface or by the object. So like I say yesterday, all object or all surfaces emit radiation, produce radiation. Okay, as long as the temperature of the surface, okay, if the temperature of the surface is greater than 0 Kelvin, so they have radiation, heat radiation exists. Okay, as long as the temperature of the surface larger than 0 Kelvin. Okay. Okay. So this equation is basically for the single surface. Okay. So for a single surface, what happens when you are dealing with multiple surface? For example, you imagine this is your, okay, this is a room. Okay, this is a room. You have an object that produce radiation because of the temperature is higher than the surrounding. But at the same time, you have this surface, okay, which is, of course, if you are sitting in the room, so basically it's a wall, okay, it's a wall, or it's a side of the room, okay. Of course, the temperature of the wall or the surface is greater than 0 Kelvin. So that means this also have radiation. This also have radiation. Okay. So how to find this multiple interaction of radiation? Okay. So basically, if we can, this equation originally come from the Q net of radiation equals to emissivity times Stefan Boltzmann times A surface Ts minus emissivity Stefan Boltzmann A S T for the wall. Oh, sorry, for the surrounding. Okay, for the surrounding. Okay, so this means these are the heat that surface, then you can use this equation, okay, at which this is a net radiation because of you have more than one surface. Okay, so Ts for the surface minus T surrounding. Okay, here this T surrounding we assume it is a wall temperature. Okay, actually to be more precise, you need to know what is the temperature here, what is the T surrounding here, what is the T surrounding here, okay, and also the other side. So that is to be the exact value. But because of we assume that in one particular closed area, so the surrounding will be same, the temperature, regardless of where is the location, okay, whether it is left, right, or on the top side. Okay, so basically if you have this kind of situation, then you need to find the Ts to the power of 4 minus T surrounding to the power of 4. Sorry, this is should be to the power of 4. Okay, we will do some example on this exercise, okay, to calculate the radiation, heat by radiation. Okay. Okay, let's we do some example related to the radiation. Okay, as well as convection. I think I want to skip this one. Okay. A heat loss from a person. Okay. So if you have a textbook, you can go to this example 110. Okay. Or if you, I think someone shared the ebooks, so you can use the ebook as well to see this example. Okay, this is a common example that probably we also in the current situation, okay, where we have staying in a room, okay, at which our temperature body is a bit higher than the surrounding temperature. Okay, so in this case, a person standing or sitting in a room that the room temperature is 20 degrees Celsius. Okay, so 20 degrees Celsius. So you may say that this temperature is basically surrounding temperature. Okay, sometimes we also use T surrounding as a T infinity. This means it is always 20 degrees Celsius for that particular room. Determine the total rate of heat transfer from this person if the exposed surface area and the average of surface temperature of the person are 1.6 and 29 degrees Celsius. Meaning you need to find the Q total of this person, how much the heat produced by a person, okay, when this person exposed to this surrounding temperature of 20 degrees Celsius. Okay, the body of the person is 29, the body temperature of the person is 29 degrees Celsius. Okay, and the value of the convection heat transfer is a 6 watt per meter squared Kelvin. Okay, so meaning here the A surface is a 1.6 meter squared. Okay, and the temperature of this person, okay, I can say the TS is a 29 degrees Celsius. And the convective heat transfer coefficient is 6. So they give the H. What is the H here? So this is the H value. Okay. So the H is equals to 6 watt per meter squared Kelvin. So again, you have to remember that convection heat transfer coefficient only applicable for a fluid. So in this case, where is the fluid? The fluid is the air. Okay, so the air of the inside the room. Okay, so what is the total heat transfer rate? Okay, so basically you can see that basically heat transfer, okay, can be analyzed by 3 methods or 3 modes. Okay, so one is conduction, convection, then the third one is radiation. Okay, so conduction, do you have a conduction here? Okay, sorry, do you have a conduction here? So if this is our system, so this is our system. Okay, so if the system touching directly or relate with the surrounding, okay, using a solid object, so that means there is a conduction. I think it's given here in the picture. So there is a heat conduction because there is some surface that directly touch to the room. Okay, so this means this human is not hanging around. So is touching the one part of the room which is the floor area. So this means there is a conduction there. Okay, there is a conduction. So this means there is conduction here. Okay, convection. Okay, convection, of course, because you have your temperature. Okay, your temperature has slightly higher than the surrounding. The surrounding is 20. Your temperature is 29. I think this 29 is not really a normal temperature. The normal temperature is 86. Okay, but just for the example, it's stated 29. So normally the temperature of our body is 36. Okay, so not really logic in this example. Never mind. But for the convection, as long as we have a delta T, okay, what is the convection? If you remember the equation, Q equals to H delta T. So if we have delta T and we have H value, you got H, you got delta T. That means this is convection, this is okay, the heat by convection is this okay, the total radiation. Okay, so Q equals to emissivity times distance times 1 times A times T as a power of 4. Like I said, as long as the TS is greater than 0 Kelvin, so this means there is also radiation. Okay, so basically in this example, so if you want to calculate the Q total, so you need to consider all the heat by heat transfer. This is Q conduction plus Q. This is the because this is a heat rate. Okay, total rate of heat transfer. So this is Q dot. If only heat transfer is a Q. Q dot by conduction plus Q dot by convection plus Q dot by radiation. Okay, so all Q you already, I mean all Q is need to be considered in this analysis. Okay. Okay. Next one you need to calculate one by one. So how to calculate the heat by conduction? Okay, how to calculate heat by conduction? Okay. So if you look to the more details area here, okay, if we can increase the size of the, they say this is the I can say this is let's say this is the shoes. Okay, so this is the 29 degrees Celsius. Okay, so this is 20 degrees Celsius. Okay, so there is some heat conduction here. Okay, so if you look here, in order to calculate Q conduction, you need to have a negative Ka delta T over delta X. Okay, let's say you don't know the A, so you can put Q over A equals to negative K delta T over delta X. Okay, so you need, okay, you might know the delta T because delta T is a 29 minus 20. You know the thickness, the shoe is your delta X. Okay, but here the K value. So what is the K value for the shoes? Okay, normally it's a rubber. So if you look to the rubber, so I have this one here in the table. You can find the thermal conductivity for the find. Let's say I try to find K value in the rubber thermal conductivity. Oh, in fact, we can find from the textbook. Okay, so we can, if we go to the textbook, actually, you can from the tables, A, what is the I hope you can. It's basically same like thermodynamics. Okay, those who, you already learned thermodynamics in order to find properties of the materials. You need to go to this table appendix. So this is table A1 for the gas. Okay, we need to find the rubber one. Okay, solid metals, we need to find non-metals. Okay, because rubber is considered non-metals. Okay, this one non-metal. Okay, solid non-metal. We have the rubber here. Okay, seems that we don't have a rubber. Pyroceramic, wood, hardboard, plywood, masonry. Roof, glass fiber. Sawdust. We don't have a rubber here. This is what? This is no. This
Come back to
fruits,
our
meats. Also, there is some food
come back to
food with the common properties. Okay, the type of food you also can use this. This is what, glass? No, this is water. So it's not available for the rubber. Then we have to find from the
So this is rubber natural.
from this one. Okay, thermal conductivity for the rubber. Okay. So it's about, okay, let's say 60 degrees Celsius. It's about 1 thermal conductivity, watt per meter Kelvin. Okay, so rubber is very low thermal conductivity. Okay, so this value, okay, so the value here for K for the rubber is near 1 watt per meter squared Kelvin. Sorry, per meter Kelvin. So the value is quite small, okay, compared to the metals or any product or any solid object that can easy to transfer it. Basically, from this we can say that if delta T, let's say delta T is how much? Delta T is 9 degrees Celsius, okay, or 9 Kelvin. So delta X probably less than how much? Less than specific. So delta X is less than in the small value. So you can see that the Q conduction will be in the small value compared to the Q convection and Q radiation. I believe so. Okay, you can say that because of the thermal conductivity is very small, very low, and delta X is also small. Okay, so you can say that the heat by conduction can be negligible. Okay, so for this reason is negligible Q conduction. But if you really want to calculate it, you need to find the thickness. You can find the the temperature difference. You need to find the K value. Then you can check. Okay, so that is for Q conduction. Okay, next one for the Q convection. Okay, for the Q convections, we can go to this equation. Okay, for Q convection, so since we have the H, we have the area, so HAS minus TS TS minus T surrounding. Okay, so the H value is a 6, area is a 1.6, TS is your temperature of the body minus the surrounding temperature. Okay, and then you got this value. Okay, I think from the textbook, if you have the textbook, the value will be how much? 86.4. Okay. Okay, that is for the convection. For the radiation, so for the radiation, so you use the equation that have a multiple layer or multiple surface. So emissivity times Stephen Boltzmann times the area, Ts to the power of 4 minus T surrounding to the power of 4. Okay. So what is the emissivity here? This emissivity is for the skin. Okay, because we are producing the, this person producing the skin, we are producing the radiation. So this one is the emissivity for the human skin. Okay, so what is the value? I think from the, there is some value here, right? Skin is a 0.95. Okay. So this is a 0.95. Stephen Boltzmann 5.67 times 10 to the power of negative 8. Okay. Surface area is a 1.6. Okay. Multiply by TS. TS is 29. So you need to change into Kelvin. So 29 plus 273 is about how much? 302. Kelvin to the power of 4 minus 20 plus 273, 293 to the power of 4. Okay, and if you look this, so the value is about 86 point, sorry, not 86, 81.7. Okay, so you can see here, okay, if you look to the textbook, the value of conduction will be negligible, okay, because of the value of the heat transfer by conduction is normally small, okay, which is a bit smaller than the convection and radiation. Okay, they don't explain in here, can be neglected. Okay, so but for the Q radiation and Q convection is comparable, is in the same magnitude. 86.4 by the convection and 81.7 by the radiation. So you can see here the heat transfer by convection and radiation is in the in the same magnitude. So you cannot neglect this heat transfer by convection and radiation if you want to calculate the heat released by the human, by a person. So in total, the heat rate for one person, okay, let's say Q conduction we assume 0, okay, because it's very small. I think if you still calculate, you will get about 1 or 2 or 3 point something, okay, if you want to calculate, because the value is very small. This one is 86.4 plus 81.7. So in total, so you will produce about how much? 168. 168.1. 168.1. Is it correct? Yeah. Okay. What? Okay. So for 1%, you are producing 168.1 watt of heat. Okay, just for 1%. So you can imagine if you have more than one, so the value will be double. So you can imagine if you have more than that. So that's why if we are gathering in a number of people in a specific room, so you will feel a bit hotter compared to the number of the people in the room reduce. Okay, so you have to bear in mind that this heat, so-called heat generation, the heat generated is mainly due to the human being. Okay, that you are producing heat by the convection and radiation. There is a small value by conduction, but we always neglect it because it is not really, the heat is not really transferred by the conduction. Okay. Okay, any question? So basically, you can do this calculation even though it is like a normal system. Let's say this is probably this is electrical appliance, okay? Because the electrical appliance will be a system that can have their surface temperature. They produce some heat, okay? It's a bit higher than the surrounding, okay? And if the area touching with the surrounding will be larger, then you have to consider the heat by conduction. Okay. This is assignment. I'm not decided yet. I will give you later the assignment. Okay, so basically what you learn in these first topics or the introduction topics, you may find that in these topics you will learn a lot about heat transfer. Okay, you will learn a lot about heat transfer. Okay, previously you learned about thermodynamics. Okay, subject the course of thermodynamic 1, or we call it thermodynamics, and applied thermodynamics. Okay, so if you still remember, in the thermodynamics we always use first law, second law, and then we do some energy balance, and we assume that there will be Q in and Q out. Okay, but how to find this Q is by using the heat transfer analysis. So here the Q will be divided, or will be classified into the Q by conduction, Q by the convection, and Q by the radiation. Okay, so whether the Q will be used in the first law or whether the Q will be used in the second law, so it will define whether from what mechanism the heat transfer can be calculated. Okay, so that is the reason why you learn the heat transfer. Okay, can skip this. So basically what you learn in this three mode of heat transfer, okay, so you have this conduction, you have the convection, and you have the radiation. Okay, the important concept or term in the conduction app, you need to know the thermal conductivity. Smaller the thermal conductivity, the lower the heat by conduction. Okay, so Q conduction is a function of K. So the lower the thermal conductivity, the lower the thermal conduction. Same goes to this convection. Q convection is a function of H value. Okay, heat transfer coefficient. Q convection. Okay, is function of H. So how to reduce or how to increase the Q by convection is by increasing the H value. For example, this example, if you look to the H value here is a 6. Okay, because 6 is normally considered as a natural convection. Natural convection of free convection. So how to increase this value? So you put some blower here. Okay, so if you put a blower here, then you will increase the H. Okay, so that's why people say, or in order to release the heat more faster, put some fan, put a fan. Blow the air. You can blow the water, the hot water. Okay, so you say that in order to reduce down the temperature of the hot water, blow it, so the temperature will go down. So actually you are increasing the H value by having the blowing effect. Okay, so this one related to the H value. This means if you go higher, it's more related to the forced convection. Okay, but if you go lower, it is related to the free convection or natural convection. Okay, so that is different between forced convection and free convection. Radiation, it is related to the emissivity, okay, as well as the temperature. Okay, anyhow, all this is affect the temperature. The higher the temperature, the higher the heat. But other than the temperature, the properties, okay, the properties of the fluid, okay, like properties of the solid, properties of the fluid, and properties of the surface emissivity, okay, will influence the radiation, the heat radiation, okay, of the object or surface. Okay, so basically what I want to say that each heat transfer mode have their own important concept. Okay, in order to understand which one is relate to the value of heat transfer. Okay, so this is just a summary of what you need to understand for the analysis of heat transfer. Okay, normally, okay, same like thermodynamics. So you need to have a diagram, okay, in order to understand from where the heat transfer going through, okay, from left to right or up to down or from the inside to the outside. So you need to draw the diagram in order to get more understand the problems, and then you need to understand also what you need to find, okay, and then again list all all simplifying assumption. Okay, for example, in this example, the previous example, there is some assumption. Okay, if you look to the textbook, okay, for this example they say that the assumption relevant steady operating condition, the person is completely surrounded by the interior surface, okay, because if because the person is in between in other surfaces, then probably the analysis is not valid. Okay, the surrounding surface are the same temperature as in the air of the room. Okay, because you have to remember that if the surface of the surrounding and the surrounding temperature is a different temperature, then the calculation will be a bit more complex. Okay, and the heat conduction through the floor, okay, through the feet is negligible. Okay, so for this reason we can neglect the heat by the conduction. Okay, so that is example of assumption. So if you look to this text, see the example of the heat transfer analysis, they will provide a kind of assumption that relevant to the problem. Okay, so you can look the assumption and it will vary from case to case. Okay, so once you define the assumption, you can find the physical properties or the properties of the system, okay, or the fluid. Okay, so this is mean properties of the uh, object, okay, or surface, whether it is a solid or whether it is fluid or whether it is a in case radiation we need a surface, okay, object or surface. So develop analysis before applying numerical value. Okay, this one is just analysis, whether you want to do the simple analysis or numerical analysis, which have probably more detailed calculation like integration or differentiation. Okay, and then answer, underline answer, probably you may do some discussion and discussion. I can put it here in discussion. Okay, because some analysis required us to give some comment. What happen if this value is changing to other value, for example? Okay, what happen if the material of this particular system is changed to other material? So you need to know what the effect. Okay, this probably related to your understanding in terms of important concept for each heat transfer mode. Okay, so like I say, for conduction, really depend on the thermal conductivity. Convection depend on the convection, heat transfer convection coefficient, and for the radiation is depending on the emissivity. Okay, a bit summary on the symbol. Probably you may realize that sometimes I use a Q, sometimes I use a Q dot, sometimes I use a small q with a Q dot. Okay, So this one is different in terms of the terminology. Okay, so Q normally related to the type of energy, which is heat. Okay, so the unit can be joule or can be kilojoule, or sometimes can be megajoule. Okay, so but it's in terms of joule. Okay, but if you want to calculate the rate of the energy, okay, the rate of energy, or is also known as heat transfer rate, it should be the energy per unit time, which is joule per second or watt. Okay, can be in kilowatt, also can be in megawatt. Sometimes also, if it is very small, you can find sometimes you are dealing with a milliwatt. Okay, if you are dealing, for example, in the case of electronics dissipation, okay, heat generated by the electronics circuit, electronics component. So it is in terms of milliwatt. Okay, so it's very small. The next one, this one heat flux. Okay, so the energy also can be in terms of per unit area. Okay, so the heat flux is known as a heat flux. Energy per unit area. Okay, so that's why if you don't know the area of that particular system or surface or object, so you can get the energy per unit area, which means it's a heat flux. Okay, so regardless of conduction, convection, radiation, all these Q is exist. Okay, the rest is a convective, thermal conductivity, and emissivity. Okay, so that is some introduction of the first chapter. Okay, any question? If you look to this textbook, there is many examples how you go through. So you have to find some time, or you have to find to look to this example in order to understand the topics of the heat transfer in general. Okay. Any question? I didn't know that someone asked about World Type Surface Management Application. World Type Surface. Kami ada World Type Surface surrounding. World Type Surface surrounding. Okay, boleh isi berapa? Saya tak tahu jauh-jauh. Tadi clear. A6 saya laju sangat. A6 rubber, which one?
Expanded rubber.
Then what and select. Okay, yes, rubber. This one, correct. Not 0.032. Expanded rubber. Oh, yeah, the K is very small. So no wonder. This books is neglect the heat transfer by the rubber. Okay. So yes. So heat transfer by conduction if using rubber. So you can see here the value is 0.032. Okay. So if you try to apply to the equation Q, I cannot draw from here. So Q K delta T over delta X. So if the K is closer to 0.032, so you can see that this value will be a bit smaller than 1. Okay, smaller than 1 watt. Smaller than 1 watt. Okay, meaning the heat by conduction is very, very small compared to the heat by convection and radiation. Okay. So you may find that, okay, I just want to show you, okay, actually there is many way to find the properties in the appendix textbook, okay. So if you look here, there is many. For example, this is several type of material, okay. This is insulating material, okay. Also there is wood. If you look here, wood, they don't have a K value, okay. Meaning if it is, they don't have a K value, meaning the value will be very small, very small. This means can be nearly to the zero. So thermal conductivity by the wood is basically near to zero, okay. So meaning the wood is very good in terms of um, insulating the heat, okay. But it's a bit expensive. You want to use a wood in the certain application. Okay, if you look to this table, can you find here this temperature? So this temperature means that all this value is only valid for 24 degrees Celsius, close to 24 degrees Celsius. So meaning this is what you need to do the assumption, okay. So for example, if you want to do some analysis at a higher temperature, so you might say that this thermal conductivity is obtained at this particular 24 degrees Celsius, okay. It's very limited, okay. Okay, how about this one? If you look to this table A4, okay, sorry, A4 is for the solid non-metal. I go to for A3. A3 and A4 is the same, okay. Okay, you look to this A3, for example, properties of solid metal. Look to this stainless steel, AISI 302. This is another one. Look to this value. What the difference between this value and this value? Okay. So I think this kind of table is a bit more detailed compared to the table in the thermodynamic textbook. Okay. So if you look here, this value only valid at 300 Kelvin. Okay. What is the value of this? I cannot.
1300.
I want to put some. Okay, it's about 27 degrees Celsius. But what is the difference between this value? Okay, I think I want to open using. Let me find a way to open using the something that I can. Okay, someone asked me. Okay, wait a minute. I try to show you the how to
Real generation from the percent effect that also
to see the example to read the table at a different
the
temperature.
wall have layers.
So what is the page number just now? 949. 949. Okay, 949. Okay, this one. Okay, my question is, so what the different, okay, you want to read this one, stainless steel. So you may find this value and you also find this value. Okay, also there is some value for this. Okay, so this one, is the value of the density Cp, K value, alpha. Alpha is a thermal diffusivity at 300 Kelvin. Okay, but this one is a value of K and Cp. Okay, at the different temperature, 400, 600, 800, and 1000. Okay, so like I said previously, K is a function of temperature. So if you look to the K value, at 300 Kelvin is a 15.1. But as you increase the temperature to 400, the value increases 7.3, 20, 22.8, 25.4. So this is the explanation what I say that the thermal conductivity is a function of temperature. Okay, as the temperature increases, the K value will also increase. So same goes to the specific heat, Cp. Okay, what is the Cp? Cp is the specific heat. What is the specific heat? If someone can answer what is the specific heat? Heat produced, okay, at the heat required or heat produced by the specific fluid or by the specific substance per unit gas for one temperature degree, for one degree temperature. Okay, so you can see the value also please use the CCP. Okay, because this value is very important in order to calculate the thermal conductivity and thermal diffusivity.
Okay, Assalamualaikum.
We will learn about Cp in more detail when we dealing with heat transfer by convection. Okay. In fact, heat transfer by conduction, transient, also we use Cp. So all this information we will use from time to time depending on the problem. Currently, we only use K. Okay. So what the reason I want to show you here, for example, you want to analyze stainless steel at how much? 500 Kelvin. So the problem asks you to calculate the thermal conductivity at 500 Kelvin. So you only have 300 Kelvin, you have a 400, you have a 600. So the 500 is somewhere here. So how to do this? Okay,
Interpolation.
same like thermodynamics. When you cannot find the value of the value that given in the tables, so the one way to define the method is by using interpolation. So same thing. So interpolation not only for the water or refrigerant, so it's also used for the any kind of properties in the thermodynamics. Okay, so you might see that whether it is valid or not. So you can see from the graph. Okay, whether you want to see valid or not, the interpolation, you need go back to the relation of the you need to go back to the relation of the K to the temperature. If the relation is in the linear motion, is in the linear relation, then the interpolation is valid. Okay, so if it is if linear relation, then interpolation, okay, is valid. But if it is in non-linear, like it is exponential or inverse proportional, okay, then it is not valid if you want to do interpolation. So if you look to this textbook, you have some a graph of K to the as a function of temperature. Okay, so if you look to this graph, it is in the linear relation. So the interpolation is suitable in order to find the value within the specific temperature. Okay, so meaning that if you want to find specific temperature, specific properties at the specific temperature, one way to do is by using the interpolation. Okay, someone asked me what happened to the radiation if the wall have two layer? Okay. What happened to the radiation if the wall have two layer? Then you have to do some it's simply you need to do two analysis of radiation. Okay, what happened to the radiation if the wall have two layers? The best, for example, if you have what is the example? Probably the glazing window. Okay, so for the glazing window, we have a several layer. Then for this reason, we have to use some concept of thermal resistant layer. Okay, we will learn this in the topic of radiation. Okay, don't worry. Next one, will the radiation from the person affect? Will the radiation from person affect the outer wall? Outer wall meaning you mean outer wall is the outer from the room or the inside part?
The outer layer, sir.
Yes, Farabi, your question, will the radiation from the person affect the outer wall? You mean outer wall is the outside from the room or inside the room?
Outside the room.
From inside the room, the outer layer of the wall.
I cannot hear your voice. Can you type in the chat box? In general, if I can say that the radiation from the person, after some time, it can affect the wall the outer layer of the wall. Okay, outer layer of the wall. Because we are studying the temperature of the inside, we're not sure what happened to the outside. Okay, but if there is a significant difference in terms of temperature, for example, if the inside temperature is 20 and outside temperature is lower or higher than this one, so of course there is a effect. Okay, for example, let's say I have to find okay. Let's say if this is the wall, okay, so let's say this is the inside, this is the outside. Okay,
Selantang.
we assume this is 20 degrees Celsius. So when it is 20 degrees Celsius, this also near to 20 degrees Celsius. Okay, this is the T outside. Okay, if the T surrounding outside, okay, let's say surrounding outside, we assume in the normal temperature 25 degrees Celsius. Okay, so this is close to 25 degrees Celsius. So since there is a difference in temperature, okay, so this is 25. Okay, probably there is a different. Okay, if I can plot it in a graph. Okay, T. Okay, so this is inside, this is outside. Okay, This is 20. So this is 25. So there is a difference in temperature. Okay. So since the temperature outside is a bit higher than the inside, of course there will be effect. Okay. So here you need to consider the heat transfer by conduction. Okay, so probably the heat transfer inside, the inside will be receive heat from the outside if the outside have a higher temperature. But if the outside is a lower temperature than the inside, probably the heat from the inside going to outside. So it depending on which temperature have a higher value. Okay, but in that particular problem, we only concentrate or we only focus the heat transfer received or produced by the person. We not really bother about the wall or the layer of the room. As long as our system is the person, the system is the person, not the room. But if you consider the room as your system, then you have to consider this effect, the conduction by the layer, wall layer. Okay. So the outer layer is only you consider the outer layer of the wall. You only consider if the room is your the system. But in the previous example, the person is our system. Then we only focus at that particular system or the person only. Okay. So okay. So basically the table the one table that I just show you is how to find the property if it is not available in the table from the interpolation method. Okay. Okay. What else? Any question? So if you look here, there is many properties. Table A3. If you go down in the, go deeper to the tables, you can see you might find the same properties like thermodynamics. Okay, yes, saturated water. Okay, see, you have a saturated water. You may be familiar with saturated water. What is a saturated water? Probably whether it's a saturated liquid or probably it is a saturated vapor. Okay. So here you have a liquid, saturated liquid, you have saturated vapor. So you can see here for the liquid you have the K value. For the vapor you have the K value, but the value for the water is a bit smaller compared to the metal. Okay, for the solid object, because this is water, this is fluid. Like I say, not a solid object have a K value. The fluid also have the K value. Okay, but the value is very small. And you have a dynamic viscosity. This one probably you are required some knowledge of fluid mechanics. Okay, so the fluid mechanics knowledge you might need to apply in this topic as well. Heat transfer, Prandtl number. I believe you might use Prandtl number in the fluid mechanics. This one as well, volume expansion coefficient. Okay, so you will learn all these parameter in the if I'm not mistaken, this one you will learn in the convection analysis. Okay, convection. So again, this one, of course, you need to do the interpolation. The temperature at 5 and 10. So in order to find the properties at the 7 or 8, then you have to do the interpolation of this all value. Okay, let's say you want to find that particular value. So the interpolation is very common in the heat transfer. Don't say that interpolation only valid for thermodynamic. So for heat transfer, you also need to do the interpolation. What I can say is, if you have tabulated data, okay, they call it tabulated data, okay. So if you cannot find the data in the table given, so one way is to do by interpolation. So all there is a tabulated data, okay. So that's why if you look, when you some student ask me whether are we really use this table, this tabulated data when we are going, when we are working outside as an engineer. Okay, depend on the environment. If you are research, if you are R&D engineer, then you may use this. Okay, but if you just manufacturing process engineer, or probably you are do some troubleshooting, you may find the value from the manufacturer. The K value for this material is this. The K value or the density for this particular value is this. You just get it what from the manufacturer. But if you are engineer that working in the manufacturer, then you need to find these properties using the tabulated data or using some application. Okay? Okay. Any question? Okay. So basically, we finished this. The table, I think the rest table is same. Okay, only the different properties like propane. Okay. There is another, this one, liquid, methane, methanol. So there is many, actually there is many tables given in the textbook. So it is very depending on problem to problems. Sometimes you are dealing with a different system with a different material. So you can use this one. In fact, what I can see that even I'm working now, I'm still using the tables, this table, this heat transfer textbook. When I want to do some research on specific material. So it's for me, heat transfer textbook or thermodynamic textbook is very useful if you are using this in the research and development area. Okay. But some people say that these properties you also can find from the internet as well. Okay. Okay, guys. I think that's all for today. Basically, we finished chapter 1. I will give you some simple assignment probably in the e-learning. I will let you know probably 1 or 2 days in the groups. So if you have a sorry, in the previous example, there is no stated that the person wearing rubber shoes. I'm assuming. Okay. Yeah, of course, the example not say that the person wearing a rubber shoes, but what I can say that the person wearing shoes, okay, and then assumption that the shoes is made by the rubber, okay, then the K value should be close to the rubber properties. Okay. You also can say that, oh, I think the person wearing shoes from the polymer or from the what do you call it? Not say a rubber, the another polymer of the rubber. So this means you need to find other material for the polymer. Okay, then you need to find the properties. This is just my assumption. Okay, I'm assume that the person wearing the rubber shoes, that then you need to find the K for the rubber. Okay. Okay, so I think that's all for today. Thank you very much for your attention. So I will go back to the where is the attendance?